want to admit to throwing things in? No.
We even still have that thing.
And I have to ask, has anyone seen the cat? Now what?
Okay, it's fun.
Black holes are big in pop culture. That's good. That's good. Well, it's a pleasure to have you here, and it's a pleasure to have Caixia here. Caixia is the Sally Watkins Endowed visiting professor of physics here, and we've enjoyed her work. Her talk about black holes and her research has always been fun to hear and enlightening, and a lot happening in this area now. So we're looking forward to hearing you. While I have the chance, Sally Watkins was, Marty can tell you more. Sally Watkins was a dean of the college. At some point she was professor of physics. I think chair of physics, is that right? At some point she's also a Catholic nun. And so she left quite a bit of money to endow scholarships and also this visiting professor position. So we thank her and her work and all that, and care for students and work in physics. So, Caixia, looking forward to it.
Thank you, Dr. Landberg. Good morning, everyone. You guys hear me? I guess even though without this, you guys can hear me. Okay. So today I would like to talk about black holes with you guys. So I'm not an expert on black hole, but I have always been interested in them, and that's why I'm here to share with you what I have learned about black holes. So basically today I will talk about what is a black hole, and where do they from, and can we see them, and how do we study them, and how many are there, are they big, and what's special about black holes. To understand what is a black hole, so we need to understand the concept escape velocity first. So because of gravity, you may have this experience. If you throw a ball upward, the ball will fall back to the ground. Now if you try harder, you throw the ball faster, the ball can go higher, but eventually it will also come back. Now imagine you can make it faster, and maybe fast enough they can just fly away, never come back. And there exists a minimum velocity for a given planet or Earth or star, so that as long as the speed reaches the escape velocity we call, it will never come back. And the escape velocity for the Earth, that's like 11 kilometers per second. So if you can fire something with that speed, so they will just fly away and never come back. So the escape velocity depends on the mass of the object that want to fly away, and also depends on the distance from the center of that star or planet. So for Earth, that's 11 kilometers per second. So for Sun, it's much more bigger and massive. The escape velocity is 620 kilometers per second. Now, because there are two factors, mass and radius. Now, if we can squeeze the Sun into like 10 kilometer radius, so the escape velocity will be 163,000 kilometers per second. So that's faster than half of the speed of light. Now, if we can keep squeezing, so if we can squeeze the Sun to 3 kilometer radius, and similarly, if we can squeeze the Earth's radius 9 millimeters, then the escape velocity will be 300,000 kilometers per second. That is the speed of light. So you need to fire the object to reach the speed of light to fly away. So a black hole have a strong gravitational field. So it's so strong that even the light cannot, the escape velocity is equal or maybe exceed the speed of light. And what does that mean? So we know that we're familiar about light travel in straight line. So you can see me when we are in straight line. But in black hole, if you shoot the light up, and they will curve back. So according to general relativity. So this is the prediction of general relativity. Space and time is together form a space-time. And when there is no matter, no energy, the space-time is flat. And if there are matter, and the matter can curve space-time, so we can visualize this curvature of space-time by a two-dimensional rubber sheet. So if there is no mass on the rubber sheet, it's flat. And if you have big mass, like maybe a metal ball, and then the sheet will be curved. And so we said matter tells the space-time how to curve, and the space-time tells the matter how to move. And now the space-time is curved. As light come by, they will not go a straight line. So they will be bent because of the gravitational field. And for the sun, the light can be bent about 1.75 arc second. So that's like 1/3600th of a degree. But for black hole, the field is so strong that the light can come back completely. So that's like 180 degrees. So the black hole have a very strong gravitational field. So actually, it turns out you can decorate your house home using a space-time carpet. This is a game shop in Paris. So they have a space-time carpet, and you can also buy space-time coffee shop. Okay, so now we know what is black hole, and depending on the mass, so there are 4 types of black holes. So black hole could be very small, tiny, as large as you, or even smaller. So that's called the miniature black hole or mini black hole. So mini black hole may form right after the Big Bang. And also there are theories predicting that the large accelerator, like Large Hadron Collider at CERN, they may create the mini black hole. But so far, no mini black hole has been identified yet. And there are also supermassive black holes. So they are very heavy. So usually all the order millions or billions of our solar mass. So astronomers, scientists, they believe that almost every galaxy, or most of the galaxy, there is a supermassive black hole at the center of the galaxy. And the most common black hole are stellar black holes. And the stellar black holes, so the mass, there is a mass limit, so there has to be at least 3 solar mass. And the recent observation also showed that there are mid-sized black holes, so between the stellar mid black hole and the supermassive black hole. Identify yet. And you may also heard about primordial black hole, so that's mini black hole. So they may be created like right immediately after the Big Bang. And so most of the black holes we found are actually stellar mass black holes. So we believe that stellar mass black holes, they come from the death of massive stars. So when a star runs out of its fuel supply, so they will die. And before they die, there will be a huge explosion called supernova explosion. And this is actually this is the Crab Nebula. So the supernova happened like 1,000 years ago. So actually, people in ancient China, people observed the supernova. And for this one, right now, when we observe at the center of this nebula, Crab Nebula, there is a neutron star. So depending on the mass of the star, and there are 3 destinies for them. So if the mass is smaller than 1.4 solar mass, at the gravitational force, gravitational will pull the mass together, there will be electron. So in quantum mechanics, there is a Pauli exclusion principle. So the electron will resist to occupy at the same location. So those electrons will create a pressure to stop the collapse. So if the mass of this center of the star is small, so the electron pressure can stop the collapse. But if the mass is higher, like between 1.4 solar mass and 3 solar mass. So the gravity is so strong, so they can push the electron toward the proton. So the proton and electron, they can form together to become a neutron. And the neutron also have the Pauli explosion. They want to prevent the collapsing. So when the mass is between this range, so the neutron pressure, they can prevent the collapse. However, if the mass of the planet, if mass of the center of the star is greater than 3 solar mass, and then nothing can stop the collapse. So gravity will pull the mass all the way together to form a black hole. So all the mass they pull together will reach one point. That's called the center of the black hole. That's called a singularity. So singularity is like zero volume and all the mass concentrated at that one point. So the curvature will be infinitely large. And the singularity usually is surrounded by a event horizon. So event horizon is like the boundary of the black hole, or you can say it's like so earlier we talked about the escape velocity. So this is the position. The escape velocity is equal to the speed of light. So if you enter a black hole past this line, you can never come back. So this is also called the point of no return. So for a spherically symmetric black hole, non-rotating, the radius of the event horizon is the same as Schwarzschild radius. So we can actually, so that's the equation for the radius of the event horizon. So we can actually, based on the mass, we can. So earlier I talked about if we squeeze the sun to 3 kilometer radius, that will be a black hole. So the event horizon actually is very small. So like for the Earth, the mass of the sun, that's just 3 kilometers of radius. And because of the strong gravity around the gravitational field, there are a lot of interesting things happen. So before we talk about what will happen if a person or object fall into a black hole, so I want to talk about the gravitational time dilation. So you may have heard about time dilation in special relativity. So if your twin sister or brother, they can travel very, very fast. And when they come back, so they will be younger than you. So that's time dilation. Like so their clock looks like tick slower as they are moving very fast. So there could also be gravitational time dilation caused by the strong gravitational field. So and for example, all the Earth and all the surface, compare the gravitational field all the surface and the high elevation. So the high elevation have a weaker gravitational field. So if we are on the Earth surface, we observe a clock that has a higher elevation, they will be running faster because of the weak gravitational field. Actually, all the Earth, like we use the GPS, the satellite, or in the sky, and so the time dilation for the satellite is like the order of microseconds. So like 30, 40, I think it's around 40 microseconds. And so this is for the Earth. So for black hole, the field is much stronger. So the time dilation actually is more obvious. So for a distant observer, so on the top of the graph there are two clocks. So one clock, the bottom clock, let's assume that's from outside observer, and the top clock is carried by an object that's falling close to the black hole. So you can see as the object getting closer to the black hole, so the clock is going slower and slower. This is from a distant observer. So actually, by the time they reach the event horizon, they will find the clock will not moving anymore. So like a time stop. So the time stands still, and so you can never watch your friend falling into a black hole. So for example, the bottom one, let's show 2%. So the bottom one, the one with the gold hair. So let's see she is Alice, and the top guy, let's see, Alex. So Alex is observing Alice falling into a black hole, and Alice, all the way to her black hole, she will send out a signal, light signal to Alex, like Alice is carrying her own clock. So let's say like once an hour, she will send a light signal to Alex, shows that she is closer and closer. Based on her clock, she send out this signal like once an hour. But when Alex receive this signal, and he find the time he receives signal actually is longer and longer, not equal interval anymore. And actually, let's suppose the last signal is sent out by Alice when she reaches the event horizon, and this signal will never reach Alex. So from Alex's point of view, Alice can never enter the black hole. So it takes infinite time for the signal to come back to Alex to show that Alice is actually falling into a black hole. So this is the time dilation, and actually, so the time dilation is from different observer. Like the clock carried by Alice herself is just run as normal. It's just from the point of view Alex, who is far from the black hole, and he think her clock is slowing down. It's at a slower rate, and actually there is no problem for Alice to fall into the black hole. And so earlier we talked about the time. So it takes infinite time for the light to reach Alex, and actually at the same time there is also gravitational redshift happening. So you may have heard about Doppler effect, and when a police car coming, and you will hear a higher pitch, and when they are moving away, you hear a lower pitch. And Doppler effect can also happen for light. So when the star is moving away from us, the light coming to us is redshifted, so the wavelength is longer. And so the redshift can also be caused, so that one is due to Doppler effect is due to the relative motion of the observer and the source. But the redshift can also be caused because of the strong gravitational field. So the signal sent out by the black hole, and they move away from the black hole, there will be red shift, so the wavelengths will be longer and longer. Fall into black hole, there is another interesting effect because will be tidal forces. So also tidal forces due to the ratio, the differential of the force. How do I say that? Like all the surface Earth, you may have heard about free fall. So we said our average, the free fall acceleration is about 9.80 km/s². However, the actual number depends on the elevation, depending on the position. It's just all the Earth, the mass is strong, the field is not so strong, so it's close to equal. But when we approach black hole, so the field is so strong, so when you fall to a black hole, the gravitational force at your foot will be much greater than the gravitational force at your head. So eventually, we call this is called spaghettification. So when you fall into black hole, you may become it will be stretched very long, become a spaghettification. Actually, this is predicted by classical physics, like we consider general relativity the classical physics, and there is actually new research like in 2012. So people talk about the quantum effect, and they think the event horizon is like a wall of fire, and when you reach there, you will be burned, and no spaghettification. I guess will be barbecue. So much mass, all of them, when they fall into black hole, so before they fall into black hole, they could be different color, different shape, different chemical structure, and maybe they are proton and neutron atom. But when they fall into the black hole, all the information will be lost. So for black hole, 3 parameters can completely describe the structure of black hole. That will be mass, charge, angular momentum. So we call this is the black hole no-hair theorem. So only 3 parameters we can completely describe them. So we can study the mass by the gravitational effect of the surrounding star or gas. And we can find the charge by studying the strength of the electric field. And the angular momentum is related to the rotation, so how fast it is rotating. And if we study the quantum effect of black hole, actually Hawking studied the quantum effect near the event horizon of black hole. So you may have heard about in quantum mechanics we have particle, anti-particle. So each particle have their anti-partner and their equal magnitude, opposite charge. And when they meet, there will be annihilation. So the anti-particle of electron is a positive positron. So when positron and electron meet, they will annihilate, emit energy. And so according to the quantum field theory, actually everywhere in the universe there is a vacuum fluctuation. So there are particle, anti-particle created and they're annihilated in a very, very short time. But when this happens nearby this black hole, and the black hole, the gravitational field is so strong, they could pull one of the particle back to the black hole. Then left with the other one. The other one can fly away from the black hole, so they can carry some energy away. And this is defined by Hawking. So we name this Hawking radiation, or we call also equivalent to say black hole evaporation. So because of this evaporation, so the mass and energy of the black hole actually could decrease. So as time goes by, the black hole will shrink, and eventually they may dissipate and disappear. And this the rate of evaporation is inversely proportional to the mass. Small mass like mini black hole, they have a fast evaporation rate, so they have a shorter lifetime. So if a black hole is not growing anymore given a certain mass because of evaporation, so they can disappear. And this is the best of the quantum effects. And the radiation you study is similar to a black body radiation. Like they also have a temperature, but the temperature is inversely proportional to the mass. So like for a stellar black hole, so that temperature is like a billionth of absolutely Kelvin degree, so very close to absolute zero. So it's hard to experimentally observe this effect. The black hole, they're black, so even light cannot come out. So we cannot observe black hole like the way we see stars and objects. And however, the black hole can show them in other ways. So the first one is the gravitational effect. So they have huge mass, and outside the black hole, they just act like a normal huge mass. So for example, if we replace the sun with an equal mass black hole, so the Earth and the planet will also move the same orbit. They won't change. It's just we won't gain the radiation, the energy from the sun anymore. Okay, so we can actually observe or predict the existence of black hole by the gravitational effects around the surrounding stars. So in the universe, binary system is very common. So it's common to a star that's surrounded with a partner with a black hole. So by studying the orbital period and the radial velocity of that star, so we can actually predict what's the mass of the other black companion, and based on the mass we can, and if it's above the three solar mass, so we can conclude that's a black hole. And actually the first object that's considered to be a black hole was found in 1971 in a Cygnus X1 binary system. So the right side, this picture is an X-ray picture. So later we will talk about how is X-ray related to black hole. So when they first receive the X-ray signal, and then they find the star have a companion. So based on the motion of the star, they predicted the mass of this black hole could be like 16 times the mass of the solar. So actually, there is an interesting story about this black hole. So this was predicted in 1971. So yeah, in 1974, and Stephen Hawking and Kipstone. So Kipstone is one of the guy who won Nobel Prize this year, and he designed the LIGO observatory. And they had a debate, and Stephen Hawking did not believe this is a black hole. So the debate started in 1974, like 26 years later, like in 1990, and Stephen Hawking said, okay, he's wrong. So he conceded his debate. We can also detect the black hole by studying gravitational waves. So recently it's a very popular topic. And the first gravitational wave signal from black hole was detected in 2015, two years ago. Actually, I think it's 2015, September 15th. So they detected the gravitational wave emitted by two stellar mass black hole colliding and merged to one black hole, and the bottom, that's the gravitational signal they received. Now let's see the computer simulation when two black holes collide and merge. So this is much more exaggerated. In reality, when they happen, actually, it's a very short time interval. So as the two black holes collide, and there will be gravitational wave.
Closer and closer together. As they get closer and closer together, more gravitational waves emerge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth. Right? And when it gets to the Earth, the gravitational wave passes. And what it's going to do is stretch and compress space as these waves pass. And you'll see that the Earth is jiggling like jello. I don't want people to be scared. The Earth doesn't really do this. This effect is greatly exaggerated, but it gives you the effect. And then we zoom in, and how we detect these are using the interferometer that's in LIGO. And Ray Weiss is going to tell you more about the interferometer. I just want to say one thing. That the effect that we're trying to measure from these violent, these big black holes colliding with each other at half the speed of light, all right, is so tiny that it takes something like LIGO to measure it. We are trying to measure things basically at 1/1000th the diameter of the photon. That's the size of the signal that you see on Earth from those events that take place 1.3 years away. Let me put that in perspective because I think.
This is from last year, 2006. They announced the detection of the gravitational wave from the talk. So I tried to cut the video, but they always have this title from the software. And so the guy, he mentioned LIGO can detect the change of the length, that's 1/1000th of the diameter of proton. So the proton size is like 10 to negative 15 meter. So that's like 10 to negative 18th meter. Detected the signal, that's the two stellar mass black hole. When they collide together, they emit the gravitational wave. So astronomers actually also find supermassive black holes at the center of the galaxy. So here, this picture shows you a galaxy. The center is very, very bright. That's very, very, very bright. And this type of galaxy, so this center, we call them it's active galactic nuclei. So it's believed that there is a supermassive black hole at the center, and the bright thing around the black hole, that's called the accretion disk. So we will see one from simulation about this. So the aging is actually the center of the galaxy. So it's a small, compact area, but it's so bright. It's actually brighter than the rest of the galaxy. So they believe that surrounding the black hole, the bright central part, that's an accretion disk. So when mass come close to a black hole, but not exactly fall into yet, and they will be accelerated because of the angular momentum conservation, so they will be moving faster and faster, and actually the relativistic speed, and they will be heated up very high temperature, and they will emit light very brightness. There could be X-ray or visible light or radio signals, and we call this is the accretion disk. So when the nearby gas or dust or even a star, when they fall into a black hole, before falling into a black hole, so they will form this fast moving disk, and the disk is heated up very high temperature, so they will be very bright. Like we talk about the galactic center nucleus, so they are the brightness. So it's believed to be powered by the black hole at the center, and like this one. And so originally, when people first detect this signal, they thought the light is coming from a point source. They didn't find the galaxy because the center is so bright, so they can't see the galaxy. I detected the signal. That's the two stellar mass black hole. When they collide together, they emit the gravitational wave. So astronomers actually also find supermassive black holes at the center of the galaxy. So here, this picture shows you a galaxy. The center is very bright. That's very bright. And this type of galaxy, so this center, we call them it's active galactic nuclei. So it's believed that there is a supermassive black hole at the center, and the bright thing around the black hole, that's called the accretion disk. So we will see one from simulation about this. So the aging is actually the center of the galaxy. So it's a small, compact area, but it's so bright. It's actually brighter than the rest of the galaxy. So they believe that surrounding the black hole, the bright central part, that's an accretion disk. So when mass come close to a black hole, but not exactly fall into yet, and they will be accelerated because of the angular momentum conservation, so they will be moving faster and faster, and actually the relativistic speed, and they will be heated up very high temperature, and they will emit light very brightness. There could be X-ray or visible light or radio signals, and we call this is the accretion disk. So when the nearby gas or dust or even a star, when they fall into a black hole, before falling into a black hole, so they will form this fast moving disk, and the disk is heated up very high temperature, so they will be very bright. Like we talk about the galactic center nucleus, so they are the brightness. So it's believed to be powered by the black hole at the center, and like this one. And so originally, when people first detect this signal, they thought the light is coming from a point source. They didn't find the galaxy because the center is so bright, so they can't see the galaxy. Actually detected the signal. That's the two stellar mass black hole. When they collide together, they emit the gravitational wave. So astronomers actually also find supermassive black holes at the center of the galaxy. So here, this picture shows you a galaxy. The center is very, very bright. That's very bright. And this type of galaxy, so this center, we call them it's active galactic nuclei. So it's believed that there is a supermassive black hole at the center, and the bright thing around the black hole, that's called the accretion disk. So we will see one from a simulation about this. So the aging is actually the center of the galaxy. So it's a small, compact area, but it's so bright. It's actually brighter than the rest of the galaxy. So they believe that surrounding the black hole, the bright central part, that's an accretion disk. So when mass come close to a black hole, but not exactly fall into yet, and they will be accelerated because of the angular momentum conservation. So they will be moving faster and faster, and actually the relativistic speed, and they will be heated up very high temperature, and they will emit light very brightness. There could be X-rays or visible light or radio signals. And we call this is the accretion disk. So when the nearby gas or dust or even a star, when they fall into a black hole, before falling into a black hole, so they will form this fast moving disk, and the disk is heated up very high temperature, so they will be very bright. Like we talk about the galactic center nucleus, so they are the brightness. So it's believed to be powered by the black hole at the center, and like this one. And so originally, when people first detect this signal, they thought the light is coming from a point source. They didn't find the galaxy because the center is so bright, so they can't see the galaxy actually. Detected the signal, that's the two stellar mass black hole. When they collide together, they emit the gravitational wave. So astronomers actually also find supermassive black holes at the center of the galaxy. So here, this picture shows you a galaxy. The center is very, very bright. That's very bright. And this type of galaxy, so this center, we call them it's active galactic nuclei. So it's believed that there is a supermassive black hole at the center, and the bright thing around the black hole, that's called the accretion disk. So we will see one from a simulation about this. So the aging is actually the center of the galaxy. So it's a small, compact area, but it's so bright. It's actually brighter than the rest of the galaxy. So they believe that surrounding the black hole, the bright central part, that's an accretion disk. So when mass come close to a black hole, but not exactly fall into yet, and they will be accelerated because of the angular momentum conservation, so they will be moving faster and faster, and actually the relativistic speed, and they will be heated up very high temperature, and they will emit light very brightness. There could be X-ray or visible light or radio signals, and we call this is the accretion disk. So when the nearby gas or dust or even a star, when they fall into a black hole, before falling into a black hole, so they will form this fast moving disk, and the disk is heated up very high temperature, so they will be very bright. Like we talk about the galactic center nucleus, so they are the brightness. So it's believed to be powered by the black hole at the center, and like this one. And so originally, when people first detected this signal, they thought the light is coming from a point source. They didn't find the galaxy because the center is so bright, so they can't see the galaxy actually. So in the video, we also see the power jets. So the jets are so powerful. And actually recent observation originally they thought so when the accretion disk have high temperature and there will be charged particle released from the black hole. Actually it's from the accretion disk, they thought. But right now they detected the power of this jet is so powerful that they may think the accretion disk is not power enough to supply this type of energy. So it's still not fully understood, and people are thinking maybe the energy is from the rotation of the black hole, but they're still studying this one. So I said the aging, they are so bright, so they are actually brighter than the remaining the whole galaxy. So the left picture that show you the bright center, and the right side is when you block that center light. That's we see the remaining galaxy here. And so the signal, this type of signal, they also call it a quasar. So when they first find the radio signal, so they are so bright at the center. And when matter, so when the matter fall into a black hole, they have the accretion disk. So because of high temperature, there will be X-ray emission, and there will also be actually gamma ray emission. So earlier I talked about the first black hole identified. So actually the first signal they detected, they find there is X-ray source, and then they point to the radio telescope and they started the orbit of the companion star and predicted the black hole. So the picture here, the pink one, that's an X-ray picture of the black hole there. So actually it's very bright. So the X-ray is from the matter of the accretion disk. And there could also be gamma ray burst. So you may have heard gamma ray is a very short wavelength, even smaller than the X-ray. So the wavelength of gamma ray is between 0.03 nanometer and 0.003 nanometer. So there are long duration and short duration. So 2 weeks ago they have the neutron star collision, the gravitational wave. They also detected the gamma ray burst signal, and they actually the reason they said that's from one reason said that's from neutron star collision is because of the gamma ray burst. That's a short duration gamma ray burst. So by studying the gamma ray pattern, so they can also conclude the mass of the objects. And here I show you one picture for hypernova. So hypernova is so compared to supernova, that's for much more heavier mass of the stellar, so more energetic, and at least over 30 times the solar mass. And you can see as the star died, the center is very bright, so that it's believed to be there is a black hole at the center. So the bright spot is the accretion disk, and you have the power, you have the very bright jets. emitting energy from there. So actually the accretion disk and the jets, so they are actually very common for like a white dwarf, for neutron star, and also for black hole. So depending on their intensity and the size, so you can tell whether they are white dwarf or black hole or neutron star. And to study the black hole, so we can use the X-ray observation. So this is the observatory X-Swift, and I've got the name. No, it's Chandra Observatory X-ray detector. So for the neutron star collision, there are signals detected by this observatory, and they can also detect the signal study the radio wave. So this is actually located in New Mexico, so not far from here. Yeah, they can also detect the radio waves. And of course, we have the Hubble Space Telescope. And okay, so when I prepared this talk, I actually find an interesting website. So before I finish, I want to show you. So we can actually travel to the black hole and see where the black hole is. Can I see this one? So the Hubble site, they have this website, so you can detect the signal. So for example, you have X-ray source or visible source or radio source, and move around and see there is a black hole or not. And then we can travel to that black hole on this website. So, okay, I think I will finish my talk at this point.
It's for Dr. Gao.
Yep.
I have a question. When a black hole evaporates, when the small one radiates away, does it turn into a white hole?
No, it will just disappear.
When it loses its mass and can no longer be a black hole,
Ah, that's a good
is that
question.
a white hole?
That's a good question. Yeah, I guess so the mass is when they form a black hole. So my understanding is the mass is already concentrated at the center of the singularity. So as the Hawking radiation happen, so the mass will decrease. So the event horizon will also shrink. So like the size will also be smaller. So it will still be a black hole, but a smaller size.
So it will shrink to infinity small.
Eventually they will disappear, completely shrink.
So the time dilation, that would come into effect on our observation of what's happening too, wouldn't it? I mean, would we be able to observe in finite time what was going on at any event horizon?
Like so.
As it was shrinking, would we be able to see?
I have the same question as the accretion disk. As mass start to speed up towards a black hole, time slows down.
Yes.
So it will take infinite time.
So that's best. Okay, so that's best a different observer. So for an outside observer, distant observer, when I watch Alice fall into a black hole, I will never see that happen. But that does not mean Alice cannot fall. She can fall into the black hole, so she can carry her own clock, and the time rate of her clock is actually run just normal at hours. So she has no problem falling into the black hole. It's just for a different observer. So the time dilation is when you compare a different observer. So the field nearby the black hole is so strong. So it takes infinite time, because it's infinite time for that signal to reach the observer outside.
Another question is the maximum density in the black hole, is at the Planck density, or it can be
density?
Yeah.
Ah, you mean the singularity?
It's a Planck density, which is a maximum, I believe.
So because of the huge gravitational collapse, they will collapse all the way to the center of the black hole. So event horizon is just a mathematical boundary. And actually, all the mass is concentrated at the center. So that's
acknowledging quantum effects at that point, or is that just a strictly general relativity calculation?
It's just from the calculation. So the singularity may be a problem. So maybe a problem with the theory. So we may need to modify the theory. But the best of the theory, yes, all the mass they will collapse to the center. So when you say black hole, the size of black hole, the boundary is just a mathematical boundary. It's the radius, so the field is so strong, like escape velocity is the speed of light. But actually, you pass through the event horizon, still nothing there. All the mass concentrated to the center. So once you enter the horizon, you will travel all the way to the center of the black hole. So it may be a problem of the theory. So the modified gravity or the theory they are trying to. So they were thinking about maybe the singularity. So there is the black hole singularity. There is also the cosmology, the beginning of the universe, the singularity. But could be a problem of the theory itself. But we don't know. Inside the black hole, we don't know. And actually, we don't know. At the singularity, I think the current quantum theory does not work either.